distribution of rocks at and below the surface. It is necessary to know what patterns of rock distribution occur naturally and what processes give rise to them in order to understand why particular rocks are present at certain depths in a borehole, and to predict from such fragmentary evidence the probable distribution of these rocks over a wider area. The distribution of rocks at and below the surface is the result of these two factors. The first one is the original distribution of these rocks at the time they were formed, and the second one is the change produced by later deformation as the rocks are buckled and fractured within the earth. Deformation may also change the character of the rock mass and its engineering properties by producing fractures or even by causing recrystallization to occur. There are two models of rocks as to studying structural geology and its dimensional distribution: stratigraphy and structural model. Stratigraphy model is the distribution of sedimentary rocks involving both vertical and lateral change of rock type. These models reflect the changes in the positional environment with place and time within one area during which sediment was accumulated. The second one is the structural model. It is the distribution of rock layers by the forming stresses produce its characteristic forms. A large part of a geologist's training is in the interpretation of three-dimensional structures of rocks from evidence collected at the surface and possibly, but not necessarily, from boreholes. A combined stratigraphic and structural model of the rocks in an area is then proposed, which is continuously refined as more evidence from surface rocks and boreholes becomes available. Strata and outcrop. Strata or stratum are the horizontal layers or beds present in most sedimentary rocks. During or immediately after the accumulation of sediments, physical, biological, and chemical processes produce sedimentary structures, and strata forms during sediment deposition, that is, the laying down of the sediments. Outcrop is a rock formation that is visible on the surface. An outcrop or rocky outcrop is a visible exposure of bedrock or ancient superficial deposits on the surface of the earth. Exposures are usually found in banks of streams, in road cuttings, on cliff or scarp faces, and in quarries. There are two types of outcrops: the inlier and outlier. Outlier is an outcrop of younger strata or rocks completely surrounded by the older strata. It is typically formed when sufficient erosion of surrounding rocks has taken place to sever the younger rock's original continuity with a larger mass of the same younger rocks nearby. Inlier is an outcrop of older rocks surrounded by younger rocks. Inliers are typically formed by the erosion of overlying younger rocks to reveal a limited exposure of the older underlying rocks. Geological maps and section. The outcrop of a body of rock, such as a layer of shale, is the area that emerges at the surface where the rock is present, or lies immediately below a cover of vegetation, soil, or other superficial deposit. A geological map is an ordnance survey map showing locations and topography on which is superimposed geological information. This includes exposures, inferred outcrops, and the nature of the boundaries between them. Any deformation of rocks, such as fracturing or other observations, and geological legend at the side of the map explaining the symbols and contours are used. Large geological departments in commercial companies and government scientific bodies, such as the British Geological Survey or BGS, have a prescribed set of geological symbols for use in their reports and maps. Each is known as a standard legend of the particular organization. Maps in this book conform to the standard legend of the BGS. The arrow is used to indicate the precise location of an exposure and the inclination or dip of any original layering or stratification. The arrow points in the direction of dip, and the amount of dip measured from the horizontal in degrees is given as a figure close to the tip of the arrow, which marks the piece location of the exposure. The observations refer only to what is seen there and not to the entire area straddled by the arrow. For horizontal and vertical layers, the position of the exposure is where the two bars in the symbol cross. Take a look at this picture. This is a block model showing the relationship between the outcrops and topography on the upper surface ABCD and the section AB. The contours at 100 and 200 meters are drawn on the map. An exposure of the sandstone layer near the river is indicated by the dip arrow, and the figure 21 beside it gives the angle dip in degrees. Here are some common symbols for geotechnical maps and plans. For general features, we have here the low water mean tide, high water mean tide, stream with arrows showing direction of flow and waterfall or height in meters, mine shaft in use, mine shaft abandoned, borehole, trial pit, surface slope up to 55 degrees, undulating slope, glacial stray with direction of ice movement, glacial stray with an unknown direction of ice movement, raised glacial feature surrounded by form line and identified by name, drumlin moraine, etc. Vertical geological section, or simply a section, is the distribution of rocks on a vertical plane comparable to an elevation in engineering drawing below a particular line at the surface. Sections are the conventional way of presenting information about the distribution of rocks below the surface. It is common practice to assist comprehension of a geological map by drawing one or more representative section below it, and to present geological information needed for planning and costing excavations such as tunnels by drawing a section along the proposed line. Nature and uses of stratigraphy. A guiding principle of geology is that the present is a key to the past. This concept is expressed more formally and more fully as the doctrine or principle of uniform materialism, which states that the process that created and molded the rocks of the earth in its past are by and large the same as those active today. Volcanic activity, which produces igneous rocks, and the deposition of eroded fragments to form sedimentary layers, proceeded in similar ways, if at different rates in the past as they do at the present time. The Earth's surface had environments, shallow seas, river deltas, deserts, similar to those found now, though not necessarily in the same places. The geography of our planet has changed continually, but the general physical conditions that may be found have remained qualitatively more and or less the same for the thousands of millions of years. The relative areas of seas, mountains, deserts, and the ice sheets have varied considerably. However, as the time passed, the principle of uniformitarianism is a particular version of one of the foundation stones at the scientific thought. That is, the premise of the same laws can be applied to understanding the distant parts of our universe, the frontliers of both space and time, as those derived from observations of Earth at the present time. The processes that have produced rocks in the Earth's past may be understood by studying how many rock types are being formed at the present. The cooling and solidification of the modern lava flow can be seen to create a layer of fine-grained igneous rocks, such as basalt. It may be inferred that similar, but older, layers of basalt are ancient lava flows and are a record of a volcanic activity in the past. Each is an event in the geological history of the area. Each different rock type is a record of the past event, and the sequence of events may be inferred using the principle of superposition. This is an example of cross-bedding rock structure. A cross-bedding in layers of sandstone. The point of the pencil indicates the original way up to the beds, as shown by truncation of the finer layering on the side of each unit. The relative ages of rocks and the structure that form them may also be inferred from other observations. For example, the presence of pebbles of granite in a conglomerate shows that the granite is older. The relative ages of rocks and geological events may be inferred from geometrical relationship from the nature of some rocks. An example of the former is shown in the figure, where the superposition of the lavas on the other beds can be seen. The fault demonstrates that the lavas are the youngest strata present. Also, the emplacement of the dike in the marl shows that the dike is younger than the marl, and the displacement of the dike by the fault shows that the fault is younger. Pebbles of the granite in the conglomerate confirm that the granite is older, and the thermal aureole in the schist shows that the granite is younger than the schist. A fossil is a preserved remains, impression, or trace of any once living thing from the past geological age. In some layers of sedimentary rock, there are traces of animals and plants that were living at the time the sediment was being deposited and were covered by sediment after their deaths. These remains are called fossils, and their study is paleontology. The common fossils are the hard part of the organisms: bones, shells, corals, skeletons, scales and teeth, and the imprints of leaves with the original vegetable matter transformed to a thin, black film of coal. Fossils are of importance as the source of what we know of past life on our planet and how it developed through the geological time. Different groups of animals and plants are found in layers of different age, and the types of fossil found in a particular layer are characteristic and diagnostic on its age. Thus, fossils, if present, provide a means of dating a sedimentary layer and a correlating rock layers in different ages by showing that they are at the same age. As a result, it may be possible to recognize a lateral change of phases, that is, a change of rock type within one layer produced at the time of formation by a change of environment across the area. We had here a simple illustrated example. Strata penetrated by two boreholes, BH1 and BH2, are shown on a vertical section. If the presence of fossils were to provide that the silt in BH1 and the sand in BH2 were of the same age, and that the sand in BH1 and the gravel in BH2 could also be correlated, then lateral changes of phases would be present in both layers. In A, the intervening vertical section between BH1 and BH2 is drawn. It shows a gentle inclination of the layering from BH2 to BH1, and a coarsening of sediment type in the opposite direction. The change from silt to sand and from sand to gravel is shown diagrammatically as interdigitation of the rock types. Life developed at an early stage of the history of the Earth, but few fossils are preserved in one older rocks. Occasionally, changes in the appearance of fossil community can be followed in detail over periods of a few million years. But typically, the fossil's record is fragmentary and disjointed. One general feature, however, stands out clearly: that life on Earth has changed persistently and gradually with time, becoming more specialized in its adaptations to different environments and more complex in the organization of individual animals and plants. These changes are described by the word evolution. Stratigraphy, the branch of science that studies rocks, especially layered rocks, brought the idea that rocks and fossils can reveal the past history of the Earth and that rock layers may be understood and interpreted in terms of past environment is an important and central concept in geology. It makes an important contribution to our knowledge of the Earth and universe, since it shares with astronomy the ability to provide evidence of events in the distant past.
The geological time scales. The strata at one locality represents only a local history of the Earth's surface. In order to compare events in layers at two different localities and designs relative ages, so that is a correlate of the strata. It is necessary to recognize similar events in both places. Distribution of rocks and below the surface, on which local events can be dated, must be based on happiness and changes that can be recognized in widely separated places. The fossil record provides such as a history assemblage of fossils in a particular environment. The characteristics of these periods of time in occurs continuously over most of the Earth. Sometimes thus elapses as a new species of an animal spreads over wider regions. From the place where it first evolved, that most examples groups have spread rapidly compared with the rates of the other geological process. The table 4.2, this pictures is the geological time scales. The age of the beginning of each period is given a million years before present. It is notable, and features of economic importance in the British are also area listed. The Precambrian. The methods used in geology depends on the process of radioactive decay, that is the disintegration of certain unstable isotopes. Most elements and they are chemically pure from the consist of more than one type of atom. So each variety, that is the each isotope, is distinguished by minor difference of atomic structures, of atomic weight, but not chemical properties. The rate of decay of unstable isotope is expressed by a half-life. This is a time taken for a half of the original parent isotope to disintegrate and produce energy and daughter products. So page T is equals, we're going to find the equations of this. So where is T is the age of, and A is the decay a constant. D is the concentration of daughter atoms and minerals due to the radioactive decay, and P is the concentration of parent atoms and minerals. So isotope used in determining radiometric age of rock should be present in a certain rock or forming minerals. Several unstable isotopes with the different half-lives are used to date rocks of widely different ages. So from early Precambrian rocks to recent the Pleistocene rice beach deposits. So distribution of rocks and the surface. Rocks with the isotopes and concentrated in mineral zircon. For rocks with a wide spread of ages, Kr can be used, particularly if the rocks contain appreciable amount of care-bearing minerals, such as micas or hornblende. Radiocarbon dating is used to date recent deposit, particularly glacials or recent beach deposit formed during the last ice age. It is also a method commonly used to date artifacts obtained from various archaeological sites. So the table point for 3. Unstable isotopes of the most important elements used to the radiometric dating of minerals. So can you read the pictures and I'm gonna explain that. So a few laboratories in every country specialize in the radiometric dating of rocks and minerals, and these laboratories have produced tens of thousands of such radiometric dates since the rocks dated from every geological area. From earliest Precambrian to late Cenozoic, a framework of limited events can be produced. So a radiometric timescales from which other events may be dated or relatively using the simple methods of traditional stratigraphy, and engineers should be understand way in which absolute ages are determined. So, strategic presentation of rocks in maps and reports. What we call this, the boundaries on geological maps sometimes define the outcrop of a single highly distinctive rock mass as such as a layer or what we call coal or limestone or dolerite dike. More commonly, as sedimentary rock layers are defined as a formation, which is bed or assemblage of beds with well-defined upper and lower boundaries that can be traced and mapped over the considerable distance. So a formation is a simple rock unit which can be dated if it contains the appropriate the fossils that define a particular subdivision of geological time. Such a rock unit may define its general properties such as a nature. Geology for civil engineers. So pebbles in the color of the cement conglomerates within it. The significant difference between the formations reflects significant difference in environment of deposition. Change of environment can so occur literally across a region of any time with corresponding lateral change of rock. Deformation of rocks, structural geology. If the structure area is known, then it's also the distribution of rocks on the two-dimensional sections across. A geological map is a generally speaking, such as sections and the distribution of rocks. In this case, the pattern of outcrops is the principal factor that may make a map more complicated than the vertical sections. So that is the letter is a planar surface. Where areas, the ground surface is likely to be irregular. In the paragraphs that follow, the qualitative and the relationship between the structures in the vertical sections are the corresponding geological map are illustrated for the different structural models. The distribution of rocks and below the surface. Interface is usually being a plane separating two different layers. A common use of a contours depict geological structures engineering geology is a counter map of rock head, which shows the depict geological structures is to solid rock in the shape of the bedrock surface. To distinguish them from the topographic contours, they are referred the stratum contours, or when they are used the certain interpretive constructions as a strike and see the fuller explanations in the what we call the six next sections. So the layer of uniform dip, horizontal, vertical, inclined strata. So original layering is the sentiments is called the stratification of bedding, or what we call the different terms are used for the layering produced by other igneous and the metamorphic purposes. Each layer is referred to as layering produced by stratum, floor, strata, or bed. The latter term is normally applied onto sedimentary rocks and volcanic ash layers. It is never applied to layer formed by basaltic or rhyolitic lava flows. So, as you can see in the picture, figure 4.5, this layer is a sandstone titled to the north at an angle of 45 degrees to the horizontal, and the clinometer has been placed on a bedding plane and oriented in north-south direction. That is a lie. Lie. I repeat, this is a lie. In the direction of maximum dip, the true is dip is observed is 45 degrees when an angle of dip is read in any other directions on a bedding plane. That is some angle B with the direction of maximum dip. The apparent dip observes is a less than 45 degrees. In the limiting case where B 90 degrees and the apparent dip is a 0. So I'm gonna call this the direction called the strike dipping layer.
This figure illustrates the layer of a naturally occurring fine crumbly mixture of clay and limestone that covers sandstones, in which outcrops of the bedding plane between marl and sandstone on the valley sides are shown. This also shows the strike lines at 400 meters from A to C and 350 meters from B to D. And when we say outcrops, it refers to the exposed rocks. Next is this figure shows the sequence of horizontal strata cut by a vertical dike and their relationship with the irregular upper surface of the block. The hill and valley are shown in the profile and are also defined by topographic contours drawn in a 100-meter interval. The distribution of outcrops on the map is similar to that portrayed on the upper surface. The horizontal layers are parallel to the contours, but the outcrops of the vertical dike is a straight line and is completely independent of the contours. Next is fold. Fold is defined as a bend or flexure in a rock unit or series of rock units that has been caused by a crustal movement. Folds frequently form near convergent plate boundaries where the rock units are under compression and the folds accommodate crustal shortening. Slowly applied pressures, either deep inside the earth where the confining pressures caused by overburden is considerable, or to non-brittle rocks, tend to produce folds through buckling or plastic flow. A fold's essential characteristic is a change in dip, and when we say dip, it is the angle at which a planar feature is inclined to the horizontal plane. Change in dip happens at the fold's hinge. On either side of the hinge is a limb with a somewhat consistent drop. The change in dip in genuine fold is rarely contained to a line but is concentrated at the liner zone. Next, this shows an aerial image of an eroded anticline in Iran that plunges at a low angle towards the top left of the photograph. On the foreground, an arc of huge limestone that is still intact in the distance has been worn away to show the pattern of outcrops, characteristic of a plunging fold. Next, in terms of geologic structures, the most basic types of folds are anticlines and synclines. The up folds are called anticlines, and the down folds are called synclines. An anticline is a type of fold that is an arc-like shape and has its oldest beds at its core, while synclines are folds in a sequence of rock layers in which the younger rock
layers are found in the center of the folds. Shale is a fine-grained clastic sedimentary rock formed from mud that is mix of clay minerals and tiny fragments of other minerals. Gray whack is a variety of impure sandstone. And in the southern uplands, an anticline and a syncline effect gray whack and shale strata. Take notice of the tension joints around the hinges. Next, on this slide, the image shows that there are two vertical sections on the left side of the slide and the map and the upper portion on the right side. The outcrops of the map are symmetrical about the traces of the axial planes. The axial plane of a fold is a plane or surface that divides the fold as symmetrically as possible. Next, in figure 4.11, an anticline plunging at an angle of theta is shown. The map shows a plane in an axis as well as the former continuation of bedding plane above the map. Next, this slide illustrates the classification and nomenclature of folds in relation to the dip in the axial plane AP, angle between limbs, relative length of each limb, and the folding style. Limb is described as the sides of the fold that display less curvature. Next is flow folding. An incompetent rock experiences flow folding when it flows in a complex way to accommodate local stresses caused by a buckling or sideways pressure from the overburden compression. As a result, the fold patterns are usually complex and so no obvious relationship exists between the folds of one folded bed and another, leading to a disharmonic folding pattern. Next, the two-folded structure of metamorphic rocks are depicted in figure 4.13. However, most folds are only roughly related to one of the structural models and are, for an instance, predominantly concentric and accompanied by flow folding where mudstone beds are present. Next, fractures in rocks. A rock fracture, it refers to any geological formation that is divided into two or more distinct parts, such as folds or joints. Fractures can occur within brittle rocks, especially if stresses is applied rapidly. A rock brittleness is influenced by the texture and composition of the rock, as well as its temperature, its surrounding pressure, and any fluids that may exist within. While both folding and fracturing may occur at the same time at shallow levels in the earth, in general, fracturing occurs at shallower level. Next, salt and evaporites have flowed laterally to form two salt plugs and a salt pillow at a depth of few kilometers in figure 4.14. During the rising of the plug towards the surface, the sedimentary layers of penetrated were compressed. In addition, the beds above it have been rearranged into salt dome, the top of which has been eroded. As the sediments beneath the plug dissolves the salt at the top, it also dissolves in the groundwater. This resulted in the creation of insoluble cap of gypsum and other minerals on the top of the plug. Next, as you can see in figure 4.15, there is a fracture in the conglomerate caused by a tension. A fracture has formed with two walls that have moved apart in direction that is perpendicular to the fracture. Instead of breaking through pebbles, the plane of failure has tracked the weaker cement of the rock to leave matching irregularities in both walls. It is common for minerals to precipitate from the groundwater into the spaces between walls. Next is figure 4.16. It shows the geometrical relationship between stresses within a material and shears that occurs once the shear strength has been exceeded. On a shear, sinistral movement is viewed as the relative movement of the far wall to the observer's left. When he looks across the fault, dextral movement is viewed as a relative movement to the right. In addition, the geometric relationship between the orientations of principal stress directions with respect to vertical directions and the fault type produced by them. For instance, when normal fault develop the maximum pressure is vertical while the minimum pressure is horizontal. The geological term dextral is known as a right lateral movement describes the opposing plate moving to the right, while sinestral is also known as a left lateral movement describes the opposing plate moving to the left. Next, the figure 4.17 typifies sandstone and a coarse-grained sedimentary rock containing fragments of the other rock layers are cut by a small fault and cracks. Some are small impact-slip faults, similar to faults in addition to the size of the horizontal displacement that occurs as a result of the movement of the rock mass along a fault.
Distribute of rocks at and below the surface. Before fault movement, A and B were adjacent to each other. The total displacement A to A measured along the fault plane is called the slip of the fault. It may be resolved into strike slip and dip slip, which are respectively horizontal and vertical components in the plane of the fault. Dip slip may be resolved into a horizontal component and into a vertical component. Sharing within fault zone has produced clay gouge from the shale and fault breccia from the sandstone. The softer gouge was weathered out. Fault in geology. A planar or gently curved fracture in the rocks of earth crust where compressional or tensional forces cause relative displacement of the rocks on the opposite sides of the fracture. Faults in range and length from a few centimeters to many hundreds of kilometers, and displacement likewise may range from less than centimeter to several hundred kilometers along the fracture surface. In some instances, the movement is a dispute over a fault zone composed of many individual faults occupy a belt hundreds of meters wide. The geographic distribution of fault barriers, some large areas have almost done, others are cut by innumerable faults. Figure 4.20. A small normal fault affecting coal measures and sandstone and shells revealed in an excavation in central Scotland. The sense movement along the fault zone may be inferred from the terminal drag of the layers. The fault zone of broken rock is very narrow. There are two types of metamorphic rocks, those that are polluted because they have formed in environment with either directed pressure or shear stress, and those are not polluted because they have formed in an environment without directed pressure or relative near the surface with very little pressure at all. Figure 4.24. Regularly columnar jointing in a lava flow on the islands of Stapa, Scotland. The jointing in the top flow is irregular inferentially because of a peculiar pattern of coaling. Figure 4.25. The granite of Pluton develops of flow texture with parallel orientation of platey minerals towards its margins. Cross joints are produced by stretching of the rock in the direction of the flow texture. Flat-lying normal faults are related to the stretching of the roof. Other features shown as marginal fissures, marginal thrust, and inclusion of orsenolites. 4.4.7 Ang conformity, overstep, and overlap. The surface corresponding to this time gap is the plane of unconformity. If there have been no earth movements other than vertical rise, fall relative to sea level, then the dip is the same above and below unconformity. Unconformity are contact between two rocks units. Unconformities are typical varied erosional surface that can represent a break in the geologic record of hundreds of millions of years or more. It called an unconformity because the edges of the layers of rock that are abutting each other are continuous. Unexpected edge of layer or layers of rock are missing due to erosion in some period and geologic time is not represented. Figure point 27 will be the sandstone resting unconformable or jointing metamorphic rocks at the plane of unconformity that separates the two groups of rocks. There is a local gap in Earth history of 100 millions of years when no rocks were formed or preserved in this part of the North. 4.5 Plate tectonics and seismicity. Seismic studies have shown that the Earth is comprised of three main concentric layers: an outer crust ranging in thickness from 5 to 10 kilometers beneath the ocean and more than 40 kilometers beneath the continents. The mantle, 2,900 kilometers thick, which is separated from the crust. The core is separated from the mantle, is also layered with an inner and outer core that would being about 3,500 kilometers in thickness. Figure 4.28 Overstep and overlap. The upper formation with angular unconformity on a lower formation. Sometimes the combination of topography and geology can produce mob patterns that are quite complicated with patches of one unit surrounded by others. An inlay layer is an exposure of older strata surrounded by younger, whereas an outlayer is an exposure of erosional remnant of younger strata that are completely surrounded by older. Figure 4.29 Layers of the Earth and a major discontinuous. More important changes may occur because part of rigid outer shell of the Earth move on the top of asthenosphere. The study of the movement of the rigid shell parts is known as plate tectonics. Plate tectonics theory dealing with dynamics of Earth outer shell, the lithosphere that revolutionized Earth sciences by providing a uniform context for understanding mountain building process, volcanoes and earthquakes, as well the evolution of Earth's surface and reconstructing its past continents and oceans.